our first speaker was Robert Rallo, who is a Director of Advanced Computational Mathematics and Data Division at Pacific Northwest National Laboratory, and he spoke on AI and machine learning for scientific discovery.
What are the data requirements to be successful in each one of these domains, and what are the performance metrics that allows us to measure the progress towards this success. And this was implemented in one of the agile investments that we had at the lab, led by Kirk Corley and Nathan Hollis. Then we have to take care of the data, and we need the infrastructure to manage in the proper way the data that all these systems are going to use. And we have developed our data stewardship system and Data Hub in particular, which is the background that allows us, the backbone that allows us to collect all the data and manage all the data that we are generating. At the theory of algorithms level, we have an ongoing internal investment, which is the Mathematics for Artificial Reasoning in Science, MARS, which is an investment that looks at these theoretical components, mathematical components of machine learning. And then we have the Data Model Convergence Initiative, which is looking at this idea of how software and hardware need to be adapted in this machine intelligence, machine learning world. So these are all the different ingredients that we have. But if we want to use really machine learning to accelerate scientific discovery, the different elements that we need to make sure that we are implementing and that we are understanding are the 5 elements that I'm showing in this slide. We need to be sure that we can provide domain information to our machine learning or machine intelligence workflows. We need to be sure that we can reproduce the results that we have. We need to be sure that all our algorithms are going to be scalable to the next generation of computers, machines, or computing architectures. We need to make sure that we can tackle the automation of some processes, and automation in terms of automatic operation of specific instruments that allows us to do interaction between software systems and experimental settings. And then the final one, which is this idea of autonomy and reasoning, which is what is closing the loop between the current machine learning approach to this machine intelligence concept that I was describing before. So if we look a little bit at each one of these components, what we will see is that we have several elements which are common to all of them. So in terms of domain awareness, what we want to do is not to reinvent the wheel and to leverage all the scientific knowledge that we have developed across the years and combine all this scientific knowledge with the data that we are able to collect from experiments. And this will allow us to develop all this discipline of physics-informed machine learning that you probably have heard about, all this general idea of domain awareness, in which we can look at how do we learn representations or how do we embed knowledge representations into our machine learning algorithms to guide and to complement the data that we can collect, how we can develop domain-aware features. So essentially how we can develop new features that take into account, for instance, the physical laws that we know in a specific physical system, or how we can embed more unstructured knowledge in our machine learning algorithms. For instance, if we are developing some biomedical applications, how we can embed this unstructured biomedical domain into the machine learning loop so that we can constrain the outputs of our systems. So this is one of the components. The other component is reproducibility. And this is extremely important because essentially when we are developing this machine intelligence workflows, we need to ensure that we are capturing the data all across the process so that we can reproduce the results that we obtain at any given moment in time. And this is especially important because most of the developments in machine learning follow this iterative process in which you are optimizing the different parameters of your algorithms, of your systems, and you need to keep track of all the different lineage, all the different generations of the workflows that you are developing, together with the data and the data alterations that you may have during the workflow development. Scalability is another important element, and we have to focus not just in how we can scale all these algorithms in the current petascale systems, but we have to look also how this will translate in the future exascale systems which are coming soon, and also looking at how these algorithms map into this world of heterogeneous computing systems with GPUs, with FPGAs, with different computing paradigms, non-von Neumann architectures, neuromorphic systems, for instance, quantum computing, how all of these elements play a role and how we can leverage all of them. So for instance, what you see here at the bottom is the results of using a generative model, generative adversarial model networks to perform parameter estimation and uncertainty quantification at the Hanford site, and looking at how this can be scaled at different number of GPUs. So essentially, it's important to make sure that we can have this proper scaling in the systems that we are building. And this is going to be, of course, an effort in terms of designing the software systems that will support this, but also designing the algorithms that provide all of these elements. In terms of automation, which is the first step towards this idea of autonomy, we need to ensure that we are able to develop this concept of edge computing, so we can provide the computing, we can move the computing close to the sensor system, close to the instruments, and we can develop virtual sensors, which are the basis of this idea of the digital twins of the instruments or processes. And also we can move towards this concept of intelligent instruments, in which the instrument is not just able to collect the data, but is also able to process this data and cross-correct the execution of the experiment if something is not going as expected. So this is automation, and we have a specific hardware that we can leverage and we can install very close to the instrument, and that allows us to do inferencing or model development quite efficiently with the few resources that we have usually in the hardware side of the instruments. Finally, the last element is this concept of autonomy and reasoning, right? So essentially, how we can take autonomous decisions, and here there are different techniques or algorithms that play an important role and that we are developing. So one of them is reinforcement learning. The next one is developing and leveraging optimization techniques in order to steer this autonomous decision process, and also causal reasoning in order to understand cause and effect relationships between the different systems. And let me show you just a few examples of some of these applications, right? So physics-informed neural networks. Physics-informed neural networks are based on the idea of embedding the physics knowledge, so domain aware, into the machine learning model, so that this physics knowledge complements the data. And we have one of the projects that we have been awarded by DOE, which is FILMS, physics-informed learning machines for multi-scale and multi-physics problems, that is looking into how this can be done, and looking especially at applications of all of these techniques at the Hanford site. Digital twins for batteries. We have other initiatives which are looking at how we can build these digital models of batteries, and how we can leverage these concepts, again, of physics-informed machine learning to have surrogate models that can cooperate together with a real system, and allows us to measure and to get information that we cannot really get easily from the real system. Different applications of AI in the field of chemistry, structure, property, activity relationships, right? Looking at different ways of representing chemistry, image data, for instance, linguistic representations in the forms of smiles, or more structural representations in the form of graphs, and how we can link all these informations into to infer the energy of a specific chemical structures or the outcome of a specific reactions. Biodegradation, domain-aware features, how we can mix together different types of algorithms in order to achieve the development of these new features, which are going to be, at the end of the day, features which are informed by the domain knowledge that we have, and that then we can leverage for extended modeling. How we can use reinforcement learning in designing new materials, right? So how reinforcement learning can help us to design the interfaces between different materials in order to achieve specific properties. And the last one, how we can embed this unstructured knowledge in the form that you can see here, which is how we can embed this in order to predict what is going to be the next stage in the evolution of a patient under a specific disease based on the clinical history of the patient, right? And again, using this idea of machine intelligence to make these predictions. So hopefully, and I hope that I will not a lot over of my time. This is just an overview of the different activities that we have, and I'll be happy to answer whatever question you have or to provide more details later on. Thank you.
Thank you very much, Robert. That was an excellent presentation. I'm sure there will be many people who would like to know more, and there will be opportunities for them to ask. One of the questions I got on the chat session was where slides would be available, and I know there are things that you may need to make sure in your institutions, and yourself and others, we will work with you to make them available as your situations permit. Otherwise, I have not seen any other questions so far. I think you did great on the timing. I have questions that I have personal interest in, but in the interest of time, I'll save them for other occasions to ask.
Good. Thank you.
Let me see if there is anybody who wants to unmute and ask a quick question if they didn't get a chance to ask on chat. All right.
Question?
Sure.
Oh, I'm sorry. I was curious to see if you can elaborate, on AI with detecting for like in healthcare industry, like for instance, cancer, breast cancer or lung cancer. Is there any way? Would you know anything about this healthcare related, AI?
Yeah, so we have different activities and different projects related to biomedical applications of AI. So for instance, the one that you are mentioning, cancer detection, we had a project looking at the early identification of breast cancer from MRI images, looking at 3D MRI images and using AI in order to do in a much more efficient way, the image analysis. We are looking also at prostate cancer, for instance, from the viewpoint of looking at the clinical history of a patient and looking at how we can predict when something is giving some indications that there could be some problem related to this type of cancer. We have been working also on different types of applications on X-ray images, looking at the processing of biomarker data. So essentially, depending on the type of data that you have, you can apply different techniques, but certainly there is a lot of activity in this space of predictive medicine, especially with cancer applications.